we was discussing about continuous time Markov chain. So for that, what we have seen that if you want to completely determine the continuous time Markov chain, then what you need to know the rate matrix Q, is it not? Because either using forward or backward Kolmogorov equations, what you have P prime T is equal to P T Q T or P prime T is equal to Q times P of T, where Pt is the matrix of transition, okay, or the transition property matrix. And the initial conditions means P of 0 is equal to identity, because P ij of 0, which is delta ij from there. And what we have seen that if you have the finite dimensional state space, so in particular if Q is your finite dimensional, then okay, the solution to this problem, it is basically a system of OD. U prime T is equal to some A T of UT. Okay. So for this system of OD, actually, if you know the fundamental matrix, so from there you have your solution, which is e to the power TQ times initial condition. So in this case, initial condition is I0 is equal to identity. So you have to do the TA, and then you can write down in a series form. So then question is whether this series is convergent or not. So as you know that for infinite dimensional matrix Q, in general it may not be possible whether it converges or not, but at least for finite dimensional it surely converges. And then how to compute this solution, is it not? So this is, I am just talking about the matrix method. So basically, yeah, one such possibility I have discussed, that if say Q is diagonalizable and all the diagonal entries are diagonalizable and the eigenvalues are distinct, so in that case you can write down a similar matrix and then you can find out your PT, is it not? Which is basically A du1t and then A inverse. What is your A? A is basically the matrix associated to your eigenvectors or so on. And A inverse exists. So what is your D1T? D1T is again the diagonal matrix with now diagonal entries now e to the power T alpha 1 up to the power say T alpha n, if alpha 1, alpha 2, alpha n are the distinct eigenvalues of Q. Okay. Otherwise, what you have to do actually, if it is not say distinct eigenvalue and all these things, so you can write it in a Jordan form. That I think you know already from your linear algebra course or maybe your differential equation course. So you write it in a Jordan form and from there actually try to calculate what will be your A and so on. Is it not? Okay. And otherwise one can do it directly using your Kolmogorov's equations to find out PT. Okay, Pij of T for any ij which lies in your state space S. Okay, and not only that, so we have seen that, so suppose your chain start with state I. Okay, so now what is the waiting time? That means the time it spends at state I before jumping to or before move to another state J. Then what we have seen that if tau I, which is a spend time at state I, then what we have seen that tau I is nothing but exponentially distributed with mean minus 1 by Qii. Okay, what is your Qii? This is basically already we have seen that this is the element of your rate matrix, which is the ith element of the rate matrix. And Qii is negative, and so 1 by Qii it's basically positive. Is it not? Less than equal to 0 Qii, so it's basically equal to 0 and so on. Okay, and then we have seen given one example of a CTMC with initial distribution. So initial distribution is given to eventually it start with state some state. Okay, and then we are saying that how much time it will spend, or is the probability distributions of your waiting time before moving to another state. Okay. And not only that, we have considered the two-state continuous time Markov chains. So from there already we have find out your PT, and from there also we have seen that what happen as t goes to infinity. So later on I will talk about, like in your say DTMC case. No, so we are talking about that Pij of n, what happen as n goes to infinity, is it not? So for sufficiently large n, and if you start with state say I, then what is the probability that you will be in state J for sufficiently large n, is it not? So to ensure that we have seen that limiting distributions and so on, and for that we have certain conditions, is it not? In particular, that if your DTMC is aperiodic, irreducible, and positive recurrent, then the limiting distribution exists. And not only that, that I can have a say measure pi j, which is called the invariant measure, such that Pijn limit n goes to infinity, Pijn is equal to pi j, is it not? So here also we will talk about the similar kind of things, but little different way. Here we also that what happens as t goes to infinity, my Pij of t. Okay, so this is also kind of the limiting distribution and so on. And then, so already from your DTMC part, we know that we cannot say that all time we have existence of limiting distributions. Okay, and I have given you necessary and sufficient conditions, if not left conditions. So here also you can expect in a similar kind of things. Okay, so that I'll come back. Before that, I'll talk about called the probability of jumps. What is the probability of that? If you start with state I, then what is in the probability of jumps to another state G. Okay. So this is probability of jumps. So what it says that probability of jumps to another state J if we starting with state I. So then what is that? This is nothing but the limit h goes to 0, probability of x at point so t plus h is equal to j, given x of t is equal to I. At time t, you start with state I, then at time t plus h, for infinitesimal time h, t plus h, so you are in state j, but in between x of t plus h means you are jumping. That means x of t plus h, it is not in my state I. Okay, that is the probability of jumps. Is it not? So then these things actually, if I write down, this is nothing but limit h goes to 0. So now this part, what you can write down, this is my same as that probability of x of t plus h, which is j, given xt is equal to I, divided by probability of x of t plus h is not equal to I, given x of t is equal to I. Okay. So now if you see these things, so then what I can find out that this is nothing but my Pij of h. So as limit h goes to 0, this things is Pij of h, limit h goes to 0, and then this is nothing but summation over k is not equal to I have Pik of h, because we are considering the homogeneous CTMC, so this holds. Okay, so now these things, what I know that this is limit h goes to 0. So Pij of h, I can write down, this is nothing but my h of Qij plus small a of h, is it not? And then I have summation over k is not equal to I of h of Qik plus small a of h. So now if you divide it by h and so on, then what I have, and using the properties of small o of each function. What I have here, this is nothing but my qij, okay, divided by summation over k is not equal to I of qik. Okay, so now these things would be minus qij by q of ii, because what I know, because summation over k qik is equal to 0, no? So the row sum, okay, so the row sum is equal to 0, and hence what I have, this is qij by qii. So the probability of jumps to another state j starting from state I is nothing but minus qij by qii. So then it stay in the state for a period which is exponentially distributed with mean minus 1 by qjj, is it not? So basically this is your state I, this is your state j. So from I to j, actually you are jumping from I to state j with probability this is minus qii by ij by qii, and then you are staying here with which for a period which is exponentially distributed with mean minus 1 by qjj. That is why actually we have seen it previously, is it not? So thus the process, in this case also you can say that the process only depends on the red matrix Q, is it not? Because either it will spend some time in your state I and then it is go to another state and so on. So here also you have seen that the probability of all these things again depending on your the elements of red matrix Q. So from here also you can say that the process only depends on the red matrix Q. Okay. Okay. So as I talk about, then I will talk about so-called the limiting distributions of CTMC. Okay. So like in here also, we can talk about the invariant measure. Okay. So I have, so that means I have a say measure mu. This is defined on S. Okay, which is my state space. So state space here actually it is discrete, no? So it may take countable, at most countable things. So it is called invariant for my given CTMC xt. What I can write down if and only that mu is equal to mu times p of t. So in particular, if we look for as a element wise, that is for j is in my state, I have mu j. This is summation over I is in my S, mu of I, and then Pij of t. Okay, this should hold for all t. This should hold for all t is positive. So now this is called the invariant measure, and then we say that it is stationary. So mu is stationary if summation over j of mu j, this is equal to 1. Okay, summation over j is in my state space mu j, that mu j equal to 1. Then we say that my invariant measure mu j, which is stationary. Okay, so let us consider one example. So consider CTMC, which is CTMC, say with state space which has two elements. Okay, with S is equal to say 0 and 1, and the transition matrix PT, which is given to you say 2 by 3 plus 1 by 3 to the power minus 3t, 1/3 minus 1/3 to the power minus 3t. 2 by 3 minus 2 by 3 to the power minus 3t, then 1/3 plus 2 by 3 to the power minus 3t. Okay, so I'm giving you transition probability matrix PT, and it is known to you that XT, which is a CTMC with say state space 0 and 1. Okay, so I want to find out whether there exists a invariant measure or not. Okay, and not only that, in this case actually one can find out that it is the stationary. Okay, so mu is stationary. So how to find out? So for that, what I want to find out? I want to find out that mu 0 P01T plus mu 1 P11T, which should be my mu of 1, and then mu 0 P00T plus mu 1 P10T is equal to mu of 0. If I know these things, means the left hand side is equal to right hand side, then we are done. Okay, means we need to guess it. Say suppose some mu, say mu1 and mu2 I have, that whether I can find out for that or not. So now I'm saying my claim is that mu, which is 2 by 3 1 by 3 is a, so 2 by 3 1 by 3 is a stationary distribution. So basically, how do I get it mu? So roughly speaking, something like that. As you send t goes to infinity, okay, then the elements, if you see here, that it is 2 by 3 1 3 2 by 3 and 1 3, okay, in the matrix, the element wise that thing. So from there actually we are just writing down in this form. That is just for the guessing. Okay, it may not be the case, or we don't know, but we need to check it. Indeed, it is a case. Okay, just I am saying that just looking at this my PT and just guess, actually I am thinking in this form that okay, send t goes to infinity in the matrix and then look at the things. So from there actually I am having because later on I will try to show that as limit t goes to infinity, this is Pij of t, this should be my mu of j, that is independent of your the initial state and so on. Okay, so just using that actually my guess is in that direction. It may not be true, one needs to check it, but looking at my PT in this form actually I am guessing. Okay, so you start with my left hand side. Okay, start with this form. What is your mu 0 P01T plus mu 1 P11T? So mu 0 is 2 by 3. And what is your P01? P01 is 2 by 3 plus 1 by 3. This is no P01. This is 0 0, no? This is 0 1 0 1. This is 0 0. So 0 1 is these things 1 3. This is 1/3 minus 1/3 e to the power minus 3t, no? And then plus mu1, what is your mu1 in this case? 1/3, and then I have p11, which is 1/3 plus 2/3 e to the power minus 3t. So now we see then this is nothing but 2/9 plus 1/9. So this is 3/9, which is 1/3, which is exactly my mu of 1. So I verified the first one. Similarly, you verified that mu0 p00t plus mu1 p10t. This is nothing but you will see that this is 4/9 plus 2/9, which is again 6/9, which is your 2/3, which is exactly my mu of 0. So mu0, mu which is 2/3 1/3 is a stationary distribution or the invariant the stationary measure, okay, for the CTMC. Okay. So here actually what I try to find out, that I look at the so-called the embedded Markov chain. So embedded Markov chain, whenever I am saying that Markov chain, that means I should have discrete time Markov chain, is it not? So basically the idea is the following, that if I define a stochastic matrix P, which is my Pij, in this way, that Pij, which is minus Qij by Qii for I not equal to j, and say Qii is not equal to 0, and 0 for I is equal to j. If I define this matrix, so what happens if Qii is equal to 0, I consider my Pij, which is equal to delta of Ij. Okay, this is by definition. So now I am considering a discrete time Markov chain with initial distribution, which is say lambda, and the transition probability matrix, this P. Then that Markov chain is called the embedded Markov chain. Okay, that means in which rate actually the transition is coming on, transition is going on. And if you think of that, that is kind of you have as a the DTMC. So in particular, I am considering say Markov chain or DTMC with initial distribution lambda. Okay. What is your lambda? Lambda is the again initial distribution of your given CTMC, and transition probability matrix this P, what I am defining these things, is called embedded Markov chain of the given CTMC. So now question is, now I am having this embedded Markov chain, which is my DTMC. Okay, so I know that under what condition for this DTMC the limiting distribution exists, is it not? So the idea is the following, that if my CTMC with say rate matrix Q and you consider the associated or the corresponding Markov chain yn, which is the embedded Markov chain. Okay. Now, if your embedded Markov chain is irreducible and positive recurrent, and now I am giving one condition. Okay, that I'll write down later. That I need certain conditions on my initial distribution. Then I can find a unique stationary distribution pi such that limit t goes to infinity pijt, which is equal to pi of j. That I will write down. Before that, I try to find out the embedded Markov chain associated to some CTMC. Okay, so basically CT, what will be your for the embedded Markov chain? Basic idea is to know what is your P. So what are the element of your P? Pij is equal to minus Qij by Qii for I not equal to j, Qii is equal to 0. So it basically gives you that at the rate matrix from the ij, because qij I have no, there is no time shown in which rate. If you look at this pij and then corresponding your the Markov chain which have this probability transition matrix P with initial distribution lambda, then it is called the embedded Markov chain. And then now looking at the properties of my embedded Markov chain, I can talk about the limiting distribution from my given continuous time Markov chain. This is the basic idea. Okay. So here is the following example. I have xt, which is a CTMC with state space say 1, 2, and say 3. This is just I wrote down for a simplicity. And rate matrix give what is your Q now? Q is say minus 5, 3, 2. You can write down by yourself 1 minus 3, 2. Only I need that that QII should be less than equal to 0 and summations all this QIJ for I not equal to j is equal to 0 and summation over j QIJ is equal to 0. So just looking at that, actually I just wrote down. And then 2, 4 of minus 6. There is nothing special about this Q. You can make yourself many Q. Okay. So find the transition probability matrix of embedded Markov chain. You will see that this is important to find out this embedded Markov chain, means at least the transition probability matrix for these things is more important, that you will see a little later. What is this P? So P11, then it should be 0. Is it not? So for I is equal to j, this is 0. All the diagonal entries are 0. And then this is Qij by Qii. So Qij means minus 3 by 5, 2 by 5. So this is because this is minus and then I have taken minus, so it is positive. That is actually I want to know, because Pij it should be equal to 0 and summation over j Qij it should be 1, that is coming from there also. So what I have, this one is 3 by 5, 2 by 5. Okay, sorry, this should be case, no? And then this one should be 1 by 3, 2 by 3. This should be what? 2 by 6. So 1/3 again. And then again 2 by 3. So now this is your P, which is the probability transition matrix, and so on. So now if we look at the transition diagram, so you can think of, no? So this is 1, 2, and 3, 1, 2, and 3. So if you look at the transition diagram, this is 1, 2, and 3. So from 1 goes to 1, this is 0, 1 goes to 2, I have 3 by 5, 1 goes to 3, I have 2 by 5. Similarly, 2 goes to 1, 2 goes to 1, I have 1/3. Then 2 goes to 3, sorry, in this direction. 2 goes to 3, it should be 2 by 3. And then 3 goes to 1, 3 goes to 1, you have 1/3, and then 3 goes to 2, you have 2/3. So now from the transition diagram, it is clear that the chain or the DTMC or embedded Markov chain is irreducible, no? Because every element is connected to each others, no? One can accessible from each others. So 1 goes to 2, 2 goes to 2 goes to 3, hence 1 goes to 3, and similarly 3 goes to 2, 2 goes to 1, 3 goes to 1, and so on. Okay, or it is directly also there. So it is irreducible. So now what I know, that it is a finite Markov chain. For a finite Markov chain, all irreducible finite Markov chain means all states are positive recurrent. So all states are positive recurrent. No, using the corollary, I have proved it in the class, means in the previous class. So the all states are positive recurrent because it is irreducible finite Markov chain, hence all the states are positive recurrent. Okay. So now, as I told you that we'll use this concept of embedded Markov chain and the properties of embedded Markov chain to give conditions that will guarantee the existence and uniqueness of stationary distributions of your underlying CTMC. Okay, so that I'm not going to prove it, but I'm just stating the theorem in this way. So let xt be a CTMC with rate matrix which is Q, and let y of n be the corresponding Markov chain, means embedded Markov chain, corresponding Markov chain. If y of n is irreducible and positive recurrent, with this condition lambda tilde, which is infimum of lambda I, such that lambda I is positive, sorry, this is positive. Infimum of lambda is positive. What is your lambda I? Lambda, which is my lambda I, okay, is the initial distribution, no? That is lambda is equal to probability of x of 0 is equal to I. Okay, which I am considering same initial distribution for my y of 0. Okay, so if lambda is positive, then there exists a unique stationary distribution. Say I denote as a pi, which should be my pi of I. Okay, for underlying CTMC. So that means that is, and not that is, and limit t goes to infinity pij of t. See, there we put pij of n in n step. There is no meaning for the continuous case, no. But in a associated meaning is that as t goes to infinity pij of t. So as long run, okay. If you start with state I at long run, what is the probability that you will be in state j? That should be given by my pi of j, which is independent of these things. So moreover, how do I find out my pi j? Pi j can be determined as solutions of the system of linear equation 0 is equal to summation over I pi j qij and summation over j pi of j is equal to 1. Okay, so from this system of linear equation we can determine the limiting distributions pi j. So what it says that when you have existence of stationary distribution, it says that you need to first find out the corresponding embedded Markov chain and then try to see whether it is irreducible, it is positive, it is positive recurrent. So now there is no question of whether it is aperiodic or not. Okay, because for the aperiodicity, what we have that if you look at the Markov chain, then what is that? That GCD of all those n's such that Pij of n is positive. Okay, but here there is no such meaning for this periodicity for the continuous time Markov chains and so on. So what I need basically, instead, I need the initial distribution. So what it says that if you consider that lambda tilde, which is infimum of lambda j is positive, where lambda j is is equal to sum of lambda j, which is the initial distributions. If the infimum is positive, then I can say that there exists a unique limiting distribution for your Markov chain, continuous time Markov chain xt. And how do you find out that limiting distributions pi j? So it is basically giving you 0 is equal to pi j of q. That means it is nothing but pi of q, where q is your given rate matrix of CTMC, and summation over j pi j is equal to 1. Okay. Okay. So let us consider one example. So I have a CTMC xt with finite state space. Yes, which is say 1, 2, and 3, and rate matrix Q, which is given by say -5, 3, 2, 1, -2, 1, 1, 3, -4. See, I can consider my previous example also, no? Same rate matrix I can also consider. So what I need basically the initial distributions. I can give you initial distribution such that lambda tilde is positive. Say I have say 2 by 3, then maybe 1 by, oh, if I put 2 by 3, 1 by 3, that is not the good idea. So if you just consider something different, which is say 1/3, 1/3, 1/3, suppose. Then the lambda tilde is positive, which is basically 1/3. And then we have already seen that embedded Markov chain, which is irreducible, positive recurrent. Hence, our theorem says that there exist a limiting distributions. But we need to find out the limiting distributions. For that, we need to solve this. Pi of q is equal to 0 and summation over qj is equal to 1. Okay, these conditions, from these conditions you can find out the unique solution. Is it not? Okay, so for this case, I am also considering the initial distribution. So lambda, which is a 1/3, 1/3, 1/3. Okay. Or you can put something different, maybe half, then 1/4, 1/4. Whatever the combinations you make, so that the total sum should be 1. Okay. So you see here, again, look at, okay. So then CTMC has a limiting distribution pi j. Okay. How to find out? So before, for that, actually what I need to find out, first I need the transition probability matrix. Of embedded Markov chain. What I should have, this is 0, then 3/5, 2/5, and then half, 0, half, then 1/4, 3/4, 0. Is it not? Okay. Again, you look at from here. So this is 1, 2, and 3. 1 goes to 2, we have 3/5. 1 goes to 3, we have 2/5. Okay, then 2 goes to 1, we have half. Then 2 goes to 3, we have half. And then 3 goes to 1, I have 1/4, and then 3 goes to 2, I have 3/4. So from the transition diagram, what we have seen here, that it is irreducible. Okay, since it is finite Markov chain, all the states are positive recurrent. Is it not? And now lambda tilde, which is infimum over 1/3, yeah, is 1/3, which is positive. Okay, so limiting distribution pi, which is my pi j, exists. So now how to calculate that part? And not only that, I have limit t goes to infinity, Pij of t, which is equal to pi of j for all j is in my state S. So something like that, one can ask something like that. So if you know that the limiting distribution exists, as I told you, that starting with state I, what is the probability that at long run, okay, that means t goes to infinity. So t goes to infinity in real sense means basically for large t. Okay. So suppose something like that, some day is sunny and then it's raining and all these things, and you are giving these probability things that, okay, knowing that it is sunny, so tomorrow it will be means the PT, one step transition matrix. There is no one step actually, just we are saying that at time t, I know that, okay, I know that at time any t, if it is a rainy day, then what will be the transition that it is at time t, it will be say sunny day and so on. So then suppose today is sunny day, what can you predict about, say, maybe 2 years later, this day it will be sunny day or not? Or what is the probability that it will be sunny day? Something like that. That means if you know that for this case, the limiting distribution exists, then I can easily conclude that, okay, so limit t goes to infinity pi j t, it should nothing but pi j. So what is the probability that it will be sunny day after, say, 2 years later? Then I can say that, oh, okay, it is my only pi j. Okay, something like that I can think of. So at least for this case, what I have, I need to find out pi. So to find pi, what I need to solve it, I need to solve these things. Pi of q, that is in matrix notation. If you look at here, this one, in matrix notation, this is nothing but my pi q is equal to 0 vector. And summation over pi j over j is in my s, which is equal to 1. So now pi of q, which is my 0 vector, and pi 1 plus pi 2 plus pi 3 is equal to 1. Or eventually pi I should be positive, means not negative. So that means if I have pi of q is equal to 0, looking at your q, so that means from here I have, no? Oh, sorry, where is q? Yeah, here. So minus 5, 1, 1 is equal to pi 1 is equal to 0 and so on. So from this equation, what I have, minus 5 of pi 1 plus pi 2 plus pi 3 is equal to 0, 3 pi 1 minus 2 of pi 2 plus 3 of pi 3 is equal to 0. And then I have 2 of pi 1 plus pi 2 minus 4 of pi 3 is equal to 0. And pi 1 plus pi 2 plus pi 3 is equal to 1. If you solve this, okay, so solving above system, this is linear system. What we have, you can check it. Pi 1 is 1 by 6, pi 2 is 3 by 5, and pi 3, which is 7 by 30. So thus I can say that limit t goes to infinity pi I1 of, sorry, p of I1 of t, which is 1 by 6. Limit t goes to infinity pi of 2t, which is 3 by 5. And the limit t goes to infinity pi3 of t, which is 7 by 30. Okay, so in this way actually we can find out the limiting distributions and so on. Okay, so now we will talk about some special case of continuous time Markov chain, that is called birth and death process. So I will talk about birth and death process. What is the birth and death process? So now I have a state space S, which is a n, means included 0. So 0, 1, 2, 3, and so on, such that the transition rate matrix has some speciality that it can have transition from state I, which can either go to the nearest one, I minus 1 or I plus 1. Other than that, it is 0. Okay, so that means my qij, which is 0 if I minus j is greater than 1. Okay, qij, which is equal to 0. So that means birth and death process, it's a continuous time Markov chain. where the transition from state I can go either to state I minus 1 or state I plus 1. Okay, so it's kind of the, if you think of the size of populations, and then when state is increased by 1, then you say that okay, the birth is birth occurs, and whenever it decreases by 1, then we say that the death occurs, something like that. Okay, that is why it is called the birth and death process. So it has a transition from I to I plus 1 or I to I minus 1. So I denote Qi, which is Q of I plus 1, and mu I, which I denote as Qi to I minus 1. That means, so this lambda I, this is the rate of your birth, and mu I, which is the rate of the birth. Mu I, which is the rate of death. So if you do these things, then my transition matrix, what I can write down Q, can be written in this form, which is minus lambda 0, 0, 0, 0, 0, and so on. Then this is mu1, and then it will be staying. What is the rate of transition from there? Because this is my lambda 1 I have, so it should be minus of lambda 1 plus mu1. Because already we know that how much time it will spend here, that already know that it is minimum time it will spend here and minimum time it will spend here. So then it is exponential distribution, minimum of exponential distribution, and then lambda 1, then that is mu1, so it should be minus of lambda 1 plus mu1, and so on. Okay, so this should be 0 mu2 minus of lambda 2 plus mu2, 0, 0, and so on. This is the rate matrix for my birth and death process. So what it represents somehow, as I say that this lambda I of h plus small o of h, it represents the probability of a birth in the infinitesimal interval, say t to t plus h. This is the probability of birth, because rate is lambda I. So lambda I h plus small o of h for infinitesimal, if you look at the length, probability of birth in the interval of t to t plus h. Okay, given that at time t, so number of birth, that means xt, which is I. Okay, so this I represents the total number of births at time t. If you denote xt, which is the total number of births at time t, then this lambda h plus small o of h, which is nothing but the probability of birth in the infinitesimal time interval t to t plus h. That means h is small enough. What is the probability of birth? So this is lambda I plus h, because lambda is the rate of birth. And similarly, I can talk about mu I h plus small a of h. Again, this represents the probability of death okay, in the interval infinitesimal length t to t plus h, again given that at xt, which is the number of population at time t, it is I. Okay, so as I said that if the number of population is increased by 1, you can think of that, okay, birth has occurred, and if it is decreases by 1, then you can say that, okay, the death happened. Okay, so death occurs there. Okay, all these things for small or infinitesimal age. In small age. Okay, so for this case. Okay, So now I can think of the Kolmogorov forward equation or Kolmogorov backward equation. So from the Kolmogorov backward equation, what we have, so what is Kolmogorov backward equation? This is nothing but P prime T, which is Q times Pt. Okay. So from this equation, what I have, that P0 J prime of T, this is nothing but, okay, so for any 0 and J, so what I have, see, this is nothing but my minus lambda 0, minus lambda 0, this is P0 J of T, and then plus lambda 0 P1 J of T. For j is equal to 0, 1, 2, and so on. And if you consider any arbitrary ijth element, ij prime of t, okay, because this is q times pt, so this is my q, I have my pt. So from there, what you have, that if you look at, this should be minus lambda I plus mu I, then pij of t, and then plus lambda I. So whenever you put as a lambda I, then this should be your P of I plus 1 times 1 and then J of T and plus mu I, which should be P of I minus 1 times J of T. This holds for all I greater equal to 1. Okay, just look at any arbitrary other things, that part actually I have. This is from the Kolmogorov backward equation. So now if you try to find out Pij, so you can find out from here, and then say t goes to infinity, what happens limit t goes to Pij. And if you look at from the Kolmogorov's Kolmogorov's forward equation, from Kolmogorov forward equation, what I have the following, that Pi0 prime of t, this should be minus lambda 0 Pi0 of t, then plus mu1 of Pi1 of t, where I is in form in your state S. And what about the any arbitrary element ij t? This should be minus lambda j plus mu j of Pij of t plus now lambda I minus j minus 1, I think. Pij minus 1 of t plus mu j plus 1 pi of j plus 1 of t. This should be for j greater equal to 1. Okay, you just check it from here. So I should have pt and q, because this is nothing but p prime t, which is pt and q. Okay, from there actually just try to find out the things. Okay, so check it whether I have write down in a correct way or not. So maybe it should be lambda I minus 1 or j minus 1. Maybe it is I minus 1, and this is I plus I plus no, I think it should be j minus 1. Okay, just check it from j is equal to say greater equal to 1. If you put it, say I is equal to 1 and j is equal to 1, and what happened from there, you look at the matrix, from there actually you will find out. Okay, okay, so I think it is j minus 1, lambda j plus mu j Pij minus lambda. Okay, so I write them in a nice way. Lambda j minus 1 Pij minus 1 t mu j plus 1 Pij ij plus 1t for j greater equal to 1. Okay. Okay. So now I try to find out the stationary distributions for birth and death process. Okay. So at least suppose all the other conditions holds. Okay, means you look at the corresponding embedded Markov chain and then it is everything is going fine there. Okay, so that means it is irreducible and then you need to find out that whether it is positive recurrent or not. And so the initial distributions is given to you. Still I need to find out the conditions in which the stationary distribution exists. So I know that stationary distribution exists if we have this condition that initial distribution, the lambda tilde, which is the infimum of lambda I if it is positive, and the corresponding or the embedded, look at the embedded Markov chain if it is irreducible, and if it is positive recurrent, then the distribution, limiting distribution exists. So then how to determine the limiting distribution? So for that, I need to find out. So this is stationary distribution for birth and death process. So I'll try to find out the conditions and then I'll stop it. So what I need to solve it, I need to solve we need to solve the following, that pi of q, which should be my 0 vector, and then summation over I is in my s, pi of I, it should be 1. Is it not? So now pi of q is equal to 0. So from there what I have, that minus lambda 0, pi 0 plus mu 1, pi 1, which is actually 0. And for I greater equal to 1, what I have, that lambda I minus 1, pi of I minus 1, minus lambda I plus mu I of pi I plus mu of I plus 1 of pi of I plus 1 is equal to 0. So just from pi of q is equal to 0, I'm just trying to write down from here. Okay. Okay. Because in this way, no. So if you look at my q, yeah. So minus pi 0, lambda 0, pi 0, mu 1, pi 1, that is equal to 0, and then in this form. So that is why actually I just try to write down here in this spot. So now if you look at the any I for I greater equal to 1, in particular for I is equal to 1, what I have from here, this is lambda 0 minus mu 1 plus lambda 1 pi 1, mu 2 of pi 2 is equal to 0. Exactly this one I have put it for I is equal to, no, this is mu 2 pi 2, I is equal to 1, and then I have this part. Okay, so this is actually equal to 0 and so on. So I put an arbitrary setup. So now if you look at from here, what I have, that mu of I plus 1 pi of I plus 1 minus lambda I pi of I. These things actually I can write down. This is mu I pi of I minus lambda I minus 1 pi of I minus 1. Is it not? Just from here. So now again this part what I can write down. So this is nothing but mu I, if you replace I is by I minus 1 and so on. This is mu of I minus 1 pi of I minus 1 minus lambda I minus 2 pi of I minus 2. And if you do these things, so what I have at the end, I have mu 1 pi 1 minus in this case lambda 0 pi of 0. So now if you look at here, see, minus lambda 0 pi 0 plus mu 1 pi 1, that is actually 0. So I have, this is actually 0. So what you have from here, that pi of I plus 1, so this implies mu of I plus 1 pi of I plus 1 is equal to lambda I of pi I for all I greater equal to 0, because for 0 already we have seen it, and that for all I greater equal to 1 I have having in this form. So from here what I have, that pi of n, this is nothing but lambda n minus 1 by mu of n and then pi of n minus 1. Is it not? Now if you replace again pi of n minus by all these things, what you have, that you have summation over I is equal to 0 to n minus 1. This is the product of lambda I, because so for n I have n minus 1, then this is mu of n. So I have then I is equal to, okay, so for n greater equal to 1, what I have this part. So I have I is equal to 1 to n then mu of I. Okay, because for pi 0, pi 1, I have mu 1, mu from 1. So it is starting from 1, but there I can have, so for n equal to 1, I have lambda of 0. Is it not? So I have this is I equal to 0 to n minus 1 pi I, this part times pi of 0. Okay. So if we have a limiting distribution, that means I need to solve this system of linear equations. So from there what I have, that the pi n I can write down in terms of my pi 0 with coefficient which is coming from the red matrix Q. So from there what I have summation. As I say, the state is from say n equal to 0 to infinity. S I have considering. So n is equal to 0 to infinity of pi of n. So this part what I can write down, this is nothing but my pi 0, and then plus summation over n is equal to 1 to infinity of my pi of n, because this holds for no n is equal to 1, whatever I have put down here. So what can write down? These things I can write down pi 0, if you take common 1, plus now this is summation over n is equal to 1 to infinity, and then this coefficient. I have summation over I product of I is equal to 0 to n minus 1 of lambda I, and then this is product of I is equal to 1 to n mu I, and then take the sum. Is it not? So now this gives you 1, no? Because if it solves the system of equation, so already we have this condition. So that means, so the stationary distribution exists if and only if summation over n is equal to 1 to infinity product of I is equal to 0 to infinity lambda I by product of I is equal to 1 to n mu I. If this one is finite, because it is infinite sum, if this is finite, then I can say that the stationary distribution exists. And if this sum is convergent, that means if this is finite, then what is my pi 0? Pi 0 should be what? This is 1 by, or I can think of 1 plus summation over n is equal to 1 to infinity product of I is equal to 0 to n minus 1 lambda I by product of I is equal to 1 to n mu I inverse. Is it not? And not only that, this is my pi 0, and what about your pi of n? This is nothing but, already I have proved it, I is equal to 0 to n minus 1 lambda I by product of I is equal to 0 to I is equal to 1 to n mu I times pi of 0, which is pi of 0 is given by in this form. Okay. So this actually I have said that suppose how to find out these conditions. So suppose I need to solve the equations pi of q is equal to 0 and summation over pi j is equal to 1. From there I am deducing. But before that you need to find out no, whether it is aperiodic, the corresponding embedded Markov chain aperiodic, and so on, and all these things. So this is in a general setup. I consider S is equal to 0 to all these things. So now, but if you see that if you have a say state space S is finite, okay, so I am considering again birth and death process. In some sense, I have Qij, the red matrix given to you, Qij, which the transitions only occurs from I to state I plus 1 or I to I minus 1. Other than that, it is 0. So in that case, if S is finite and suppose I have lambda is positive, mu I is also positive for all I. So if lambda is positive, mu I is positive, then you see that the corresponding embedded Markov chain, it is irreducible. So for lambda is positive, mu I is positive. Basically, if you see that you have the transitions from one to there, there to there, there to there, and all these things. Okay. So corresponding Markov chain, embedded Markov chain, then it is irreducible. And also it is positive recurrent because of the finiteness. Okay. Hence, and lambda I is positive, mu I is positive, so I can find a stationary distributions for xt. So I put as a remark. So if state space S is finite and such that this thing holds for I is in my S, then the embedded Markov chain is irreducible. You can again draw the transition diagram and so on, and positive recurrent. See, I think whenever I am giving this lambda mu is positive, so for that case it is using the transition diagram, it is easy to find out the whether it is irreducible or not. But only thing is that whether the chain is recurrent or not, the positive recurrent or not. But since it is a finite Markov chain, that is the main part one needs to look at. Suppose it is a positive recurrent and so on. And then since lambda is positive, mu is positive for all I is in S, so the initial distributions, if you think of t is equal to 0 also, that is positive, hence I can have existence of stationary distribution. For the given CTMC, say pi, suppose I have pi 1, pi 2 up to pi of m, so S is basically 1 to up to m, and one has pi I, which is lambda 0, lambda 1 up to lambda I minus 1 by mu 1, mu 2 up to mu I of pi 0, 1 to up to m. I'm just restating that the same thing else. And pi 0, which is now 1 by, that is the inverse, no? So 1 by 1 plus summation over I is equal to 1 to m. Because for m finite, this sum is always finite. So it is means convergent in that sense. So for a finite Markov chain, means for a finite birth and death process case, for a birth process which has a finite state space with lambda mu I is positive, always limiting distribution exists, and that is given by in this form. Okay, which is lambda 0, lambda 1 up to lambda of I minus 1 by mu 1, mu 2 up to mu of I. Okay, so I'll stop now, and the next lecture I will talk about a special case of that is sometimes called the linear growth in immigration and so on. So if my lambda n has some special properties and so on. Okay, so that I'll talk about these things. Okay, so today I'll stop now.